It's just a science project.
Silent breed is people!
You know, a doctor friend once said the same thing to me. Frankenstein was his name.
It's alive! It's alive! It's alive!
That sounds like something out of science fiction.
Please explain to me the scientific nature of the whammy.
We live in a spaceship, dear.
So? Yes, science!
Program complete. Enter when ready.
Hello and welcome to episode 236 of Science on Top for Sunday the 31st of July 2016. I'm Ed Brown and with me today is microbiologist Dr. Shane Joseph.
G'day.
Science teacher Penny Dumsday.
Hello.
And Lucas Randall.
Hey.
And today we'll be looking at how and why the turtle got its shell and a new cancer treatment involving bacteria. But first, the surface of Mars seems to be an endless curiosity. As every few months...
I see what you did there.
Curiosity. Well, every few months we seem to get a new paper or an idea as to how different formations were caused. One of the most fascinating puzzles is about a good number of gullies that look very similar to gullies created on Earth by flowing water. And we've talked before about the recurring slope lineae, which are gullies that are maybe caused by periodic flows of salty water, or even cooler, by boiling or popping water under low pressure. But these are other gullies that we're talking about now, Lucas, and they seem to be not caused by water at all. Is that right?
Yeah, well, I mean, the expectation was that they were probably caused by water from much the same process that we're seeing with the recurring slope lineae, which is, as we've discussed on the show before, I think we've had a discussion maybe with Helen about this before on the show. These features have been quite striking from space-based observations, indicating that I'm talking about the recurring slope lineae here, where it looks like there's water that's basically seeping out of the soil and sort of running down the sides of hills. So we have covered that before, but these gullies are different. These gullies are apparently very widespread on Mars, and they're typically between the 30 and 50 degree latitudes in both hemispheres, both North and South Hemisphere. And they also mainly occur where hillsides or slopes are facing, towards the poles. So the expectation or the posit has been that perhaps these are also being caused by free-flowing water, and it's been frustrating because they haven't been able to spot any free-flowing water apart from these recurring slope lineae. So the reason why we know there must be something actively maintaining them is over time, because of the wind and dust and so forth on Mars, they would tend to even out. They wouldn't be quite so striking. So you'd know, if these were features that were left over only because of running water that was, millions or even billions of years ago, you wouldn't expect them to be quite so obvious now. And you also wouldn't expect them to change. And there's been some that have, have got longer or wider, whatever, over the time that we've been watching. We just haven't seen them actually, being formed, which is frustrating. So what's happened now is that they've taken a fresh look at some of these areas using the HiRISE camera on the Mars Reconnaissance Orbiter. So MRO has got a series of instruments on it, and HiRISE is one of them. And one of the cool things they're able to do with HiRISE is they're able to use it to show changes in areas over time, and also able to use the instruments to figure out the chemical composition of what it's looking at. And I'm not entirely sure of the processes that they have available to them to do that. I know of various options, but I can't actually recall whether it's just HiRISE that's doing this or other instruments that they're using on MRO to provide it. But what they did note from these observations is that there don't appear to be the signs that you would expect to find if water was behind this process. You would expect to find certain chemical compositions, you would expect to find certain clays and hydrated materials, and they're not finding that anywhere, like none. And the fact that they're not seeing these certainly seems to rule out recent flowing water as the process that's involved here. What is a little frustrating is they don't really know what it is, what it could be. One of the other possibilities, because they have noticed before, is that they have seen carbon dioxide frost forming in galaxies. So in gullies, not in galaxies. That's a different camera altogether. So It's possible that maybe that's involved in the process, but they don't really know as yet. But I think this just jumped out because it was one of those stories that I do like to revisit things when we find out more, and certainly the follow-up observations here are potentially ruling out one of the hypotheses, which is always good. It's a crawl towards knowledge.
Exactly, and that's what science is. It's ever updating. Learning and knowledge. I guess the next question is, what can they do to figure things out? I mean, is there about different equipment there to monitor it, or just hoping to catch something in the act?
We've discussed before that one of the gotchas with this is you can only do so much with space-based equipment because, effectively you're using either, radar, you're using
spectrometry,
optical observations. You can use spectrometry, but you actually need something to create the spectra in the first place. So that's something that's quite difficult, and that just actually overlaps with another story about Mars that we saw this week, actually, which is that the Mars Space Laboratory Curiosity has been basically they've changed its parameters so that it can now operate its own laser to shoot at rocks, which creates basically it causes them to vaporize, and then it can use its own spectrometer to analyze the composition of those rocks. So that's something that you could do, but the gotcha, of course, is that when there's water involved, there's a high possibility of life, we think. So as we discussed on the show before, sending something like Curiosity to these places, because they are numerous, is a problem because it hasn't been subjected to the intense processes that are required in order to ensure that there's no bacteria that hits to ride over there from Earth. So,
not to mention it's now vaporizing the rocks that might have the life on it. That's a bit rude of it.
Well, we're talking about a minuscule hole here, not like pointing a laser and disintegrating the entire thing.
Yeah, come on. Yeah. What are the odds of it not hitting the exact little bit of bacteria, the only remaining life on Mars, and we vaporize it?
Clinging to the edge of survival for 4 billion years.
That 2 millimeter diameter of rock that just happens to be the bit the Curiosity hits, of course.
Yeah.
Stranger things have happened.
So that's one thing you can do with MRO. They do have a spectrometer. I'm just not sure whether it was used in this particular observation. But here we go. Actually, I just found a paragraph which shed some light on this. Lol. Because let me read this to you. Because different chemical elements absorb light differently. It's possible to read light coming from an object to see the different elements present therein with an instrument called a spectrometer. So the team aimed another of MRO's instruments, there we go, it was a different instrument, at the Gullies, the Compact Reconnaissance Imaging Spectrometer for Mars, or CRISM, and that's what gave them the spectra. So that was how they were able to come up with the chemical composition. That's good because that was confusing me because I thought HiRISE was optical, and it is. It was a different instrument.
It is.
So there you go. But there's only so much they can do with that process. So they're using light absorption here, which is a slightly different thing that they're looking for. But if you could get something there that could actually do what Curiosity does and actually vaporize some of these rocks, you'd get a very detailed spectra, which is the whole point of that instrument. Maybe Mars.
So we just need to send another Curiosity over,
right? And that's happening now. So it's certainly on the drawing board. So
but it needs like a laser gun, like a
it'll need a laser
phaser,
and it will
sort of
Indeed.
Set to stun.
No.
In case that one last bacteria.
Yes.
Yes. So it's a hard one to answer, and of course we've got several spacecraft orbiting Mars that are always looking down, and of course, Ed, you'd recall in our visit to the Canberra Deep Space Communications Complex
Network.
Funnily enough, I saw the director on TV the other day, Glenn.
Glenn Nagel?
Yes, yeah, he was on a documentary I was watching with my son. It's like, I know him. I've met him. But that facility is involved in the tracking and communications with those spacecraft, which is kind of cool. But we don't really have anything there at the moment that we could get a greater understanding of these processes, but it's only time. It's just a matter of time, and we'll get there.
Yeah. I look forward to President Trump initiating a series of probes to Mars to get to the bottom of...
Yes.
Sorry, I've done it again.
We need to probe Mars.
Politics.
We need to make Mars safe again.
Build a wall.
Build a wall.
Around Mars?
Or
doesn't matter.
Central to Mars. He's very
that's
orange.
I think,
He'd fit right in there.
Camouflage.
We'd never find him again.
I'm cool with this.
Change approved.
I think we should move on. This is getting into dangerous political territory. So let's move on and talk about cancer. And, something happy.
What, comparatively happy?
That's me, we're all laughing.
So modern chemotherapy drugs are improving all the time, but they have really nasty side effects still. But a study published this week in the journal Nature shows some promise of being able to deliver chemo drugs directly into a tumour, thanks to some genetically modified salmonella bacteria. And that would obviously lessen the side effects that the rest of the body would be exposed to, wouldn't it?
Yeah, it would. Now, bear in mind, this study, as with all these sort of pioneering studies, has only been tested on... Well, it's been tested in vitro on human cell lines, and it's also been tested in vivo, which means on an actual animal, but again, animal, a mouse model.
So in a petri dish and in a mouse.
But not a petri dish. But anyway, it doesn't matter. But it's been... They tested this on colorectal tumours in mice, so yeah, what it sounds like, basically. And the interesting thing about this is that they're using that the very old, well, the mechanism that's been known about for a very long time called quorum sensing. Now, I think I've talked about quorum sensing on the show in the past.
You have, and it was fascinating.
Yeah, it's actually really cool. And the idea is obviously, like in a political meeting where you have quorum, where you have a certain amount of people that will enable you to go into the next task or talk about the next point or whatever. The same sort of thing applies here. Bacteria have to reach a certain cell density in the environment before they will detect a certain level of molecule that all of them are producing that will then switch on a whole cascade of other genes. Now, the very common example that gets brought up is biofilms, where you get, basically disparate, separate bacterial cells forming into one big three-dimensional structure. Like, so, for example, like bacterial slimy films that you get in ponds and things like that, that will be biofilm formation, where all of a sudden the bacteria start acting as almost like a multicellular organism. And there's obvious advantages in that. Quorum sensing is also very important for things like certain pathogenicity of bacteria. And the really cool thing about it is that it doesn't always have to just be within bacterial species. It can also cross species boundaries. So you can get multiple different kinds of bacteria working as one. Yeah, it's really cool. That's cool. But the idea here is that it's simpler in some ways. So you get this bacteria, salmonella enterica, which will encode en masse basically a cell lysing molecule. Now, obviously, one single bacterial cell is not going to do anything to a big tumour. But the idea is that they're all sitting there together and they're all producing these signalling molecules. And as soon as they reach a certain amount, they will lyse and they will basically kill themselves. In doing so, they'll release basically more lysing molecules that will actually hit the tumour cells and shrink them and attack them. So
okay, so one bacteria on its own can't do anything against the cell wall.
Or against the big massive tumour cells. Yeah.
But if you get maybe 100 or 1,000 even...
Well, like a few million, but yeah, whatever. That's I think anyway, that's, probably right.
That's even cooler. But altogether, and they recognise that there's enough of them to do this, and then they self-destruct and release.
And the important thing is that you've engineered these things to do that. Like normally they would do something else, like infect the person or whatever. But because now Salmonella enterica is, from what I know, it's a gut bug. Enterica being the formative word here, but if you engineer, so I think normally it probably would be one of those opportunistic pathogens, which if you get a certain amount of them, it'll probably turn on all sorts of virulent strains and infect you. But in this case, these strains have been just engineered to lyse. That's their only function. So they get to a certain level and they kill themselves.
That's pretty cool.
And then they release other toxic things. And then the important thing here is that they can't then go on to infect you further. Because they're dead. Now, a few cells will survive and they will start the whole process again. They'll grow and grow and grow until they get to a certain critical mass, and they'll lyse again. So, yeah.
Okay. Well, that doesn't sound good if a few survive and go on to multiply and then destroy more cells.
Yeah, I mean, that is the problem, I suppose. But it's, yeah, here we go. Few bacterial cells that don't execute the self-reproduction, yeah. So the cycle, so basically as you have a tumour. Now, I suppose then you'd have the proof of, well, the idea, I suppose, here would be as soon as you have no detectable tumour left, you would then go on a course of antibiotics to get rid of the bacteria that are infecting you. I guess that's how this would work. Now, again, this is obviously only a proof of principle study. They've only done this in mice, but that's the general idea. I mean, these ideas of using bacteria as therapy have been around for a long, long time, but we've never really.
Well, they're essentially delivery vehicles generally,
and that's the idea. I mean, we've
or
never
synthesizing material.
Yeah, and you know, I mean, it's the same sort of principle as using viruses for this thing. The difference is that viruses can't grow on their own. So in this case, if you've engineered a strain just to do this thing and this thing only, you can control it a bit better. And the great thing about this is that this certain bacteria, salmonella enterica, because it's a gut bug, it can grow in the presence of very little or no oxygen.
Right.
Because your gut is basically an oxygen-free zone. So tumour cells, apparently, because they're so, there's a big mass of them, they're basically oxygen-free zones themselves. So the idea is that here they grow very happily around those. And they sort of cluster around those areas, and then they release that hemolysin, which is the cancer drug, when they lyse themselves after they reach a certain critical mass. So it's a really nice little system, and hopefully it goes somewhere.
Yeah. Let's test it on some humans now, or at least some monkeys or something.
Well, I know that if I think if I had, say a fatal cancer, and if someone said to me, "Hey, do you want to try this?" I'd be like, "Yeah, cool." What have I got to lose, really? So.
It depends on the severity of the cancer. Obviously.
As I said, like a fatal cancer.
Yeah. All right, very cool. Well, Penny, it seems obvious to assume that turtles have evolved shells over millions of years as a form of protection. It's a suit of armour that you can hide in and be relatively safe. But Tyler Lyson from the Denver Museum of Nature and Science has been studying turtles, and more importantly their prehistoric ancestors, and he's come up with an intriguing idea about why they evolved shells.
So instead of for protection, the new idea is that it might have evolved for digging. And
what?
Yeah, I know, because when you look at a turtle now, you see it shrink back into its shell. I mean, how could it be anything but defensive?
They don't dig on their backs.
But turtle shells are actually both above and below. And there's a couple of different theories about how they evolved. Did they evolve from sort of scaly structures called osteoderms, which is what crocodiles have as their armour, or were they ribs? And it turns out that they've evolved from broadened ribs. So for most tetrapods, we have our rib cage, which rises and falls as we breathe, and the ribs can move separately and so on. However, for turtles, the ribs have become wider and fused with each other, and this happens on both sides of them. So that's really interesting, and there's fossil evidence of this process happening. First of all, it was the bottom ribs and then the top ribs. And this is actually not necessarily a really good thing, because if you just touch your chest and breathe in and out, your rib cage moves. So an animal with fused ribs is not as good as breathing. It's
kind of limited.
Yeah.
Especially one that has to hold its breath when it's swimming.
So it means that there's a payoff in terms of inflating and deflating lungs. And also the way that reptiles walk. You know how there's that really characteristic sort of lizard walk?
With the arms and legs out by its side.
Out by its side, the whole thing sort of walks. Yep. But turtles can't do that. They can't bend their trunk. So only their legs are walking, if that makes sense. I mean, I know that sounds silly, but their bodies
their legs are moving their entire bulk along.
Yeah. So that's why they're so slow. So it just seems that if it was more important for protection, maybe osteoderms, which has like crocodiles have done with that, but the bony scales would be a better way to go, because it wouldn't compromise these other things. Like by So what's the good of a shell if you're completely slow and you can't breathe? But
I guess that's why the natural assumption is that it's an armour thing, that you can't outrun your predators, but you can hide from them.
But what actually triggered this digging idea, as far as I can tell, is actually a fossil find of a Untosaurus fossil, I think that's how you pronounce it, in South Africa, which preserved the whole body. And it really looked like its limbs were adapted for digging, like really sturdy limbs. It had a really short skull. It had great big hands and big shoulder blades for attaching big triceps muscles too. So everything that would be really good with digger. So it could be that the thick shells helped to support it during burrowing. Was this something that the really, really ancient sort of proto-turtles, which only had a partial shell, were doing? Did the wide ribs help support them digging? Because nowadays turtles' shells do have a very defensive value, but that doesn't mean that that's why they evolved. Because things can evolve for one purpose and then be co-opted to do something else. So,
sure,
saving some pretty exciting fossil finds. I mean, I'm sure this is one of those many things that will just go back and forth in the literature. I don't have enough information to make an informed call myself. But the more fossils, as usual, especially well-preserved ones, I mean, we might get to know a bit more.
Am I right in saying, I'm sure I read in this article that one of the oldest fossils where they've got like those turtles with half shells, aren't they on their bellies, not on their backs?
Yeah, on their bellies.
So if it were a protective measure, surely it would be more logical to have it on their back rather than their fronts.
Yeah, exactly. That sort of pays a bit of a bit of proof as to why they weren't evolved as protective mechanisms.
Unless there were some freaky creatures that suddenly would spear them from underneath.
Or they go flip on their back and go, yes, my belly is strong. I don't know.
Well, that's how magpies and that attack cane toads. They flip them over and get the soft flesh on the belly. So maybe turtles were constantly being flipped over by giant magpies. Probably not.
Pick that, you little bastard.
Yeah, should have left me on my back. Oh no, my secret's out. But no, that's cool. I love these stories of, you know, the pervasive wisdom has always been this. It makes a bit of sense, and then someone goes and thinks outside the box and says, "But why would this have happened that way? Surely there's something else." And then you start going,
well, I mean, if you had,
all the evidence adds up.
If you had no fossils of old turtles or tortoises,
true,
you would automatically. Like, it would be I think a fairly it makes sense to think that that's for protection.
Yeah.
If you didn't have this fossil record that suggests otherwise, I think it would be fair to assume that it was basically a suit of armour. But because you've got these species that don't appear that doesn't appear to be the function at all, you have to second guess it.
Yeah, very cool. And I think we'll leave it there. For more information on the stories we talked about, you can check out our website, scienceontop.com/236. You can leave a comment there or on social media. You can also email us, feedback@scienceontop.com, and please leave us a review on iTunes. Thanks everyone for joining me today, Shane, Lucas and Penny.
No worries.
You're welcome.
Thanks, Ed.
This episode was edited with pluckiness and spunk by Marcos Benamu. Thank you everyone for listening. We'll be back again next week, putting science on top of the agenda. Join us then.
Planet Earth, this place that we live, is a beautiful and fragile place. And I take great comfort, optimism from the fact that the more we learn about nature, the more we understand questions such as how did life on Earth begin, I think the more we begin to realise that we're extremely fortunate to live on a world like this. And I genuinely think, although it sometimes sounds naive, but I genuinely think this, that the more we can explain what we've discovered as scientists about the way that the world works, the more everybody will enjoy learning that, but also learn to value the planet. Knowledge about our place in the universe makes it more likely that we'll learn to work together, value the planet, and survive to ultimately, I hope, explore the stars.